Welcome to video on analog electronics laboratory. So in this video we will see DC power supply design. So second part of it. In the previous case we have did the design of DC power supply using half-wave rectifier to get a 5 volt DC signal. So in this particular second part we will see how do we use full wave rectifier using two diodes as well as the bridge circuit. Okay, these are the prerequisites you should know to understand this. Okay, MOSFET basics may not be required here. Okay, with these introductory remarks, let us move on to 5 volt DC power supply design. Let us start the design. Okay, let us first write the circuit diagram corresponding to realizing a 5 volt DC power supply. We know that the input is an AC signal, which is at 230 volt 50 hertz AC, and it is given to a step down transformer. This is a step down transformer, and since we are looking for a full wave rectifier with two diodes, so I have to have a center tap for this. This is diode D1, this is the second diode D2. Let me show this and this go here, and this is the filter capacitor. I will write the regulator here. This becomes the reference ground 7805. So here I'll be getting plus 5 volt provided if I satisfy all the conditions. So here this will going to have a resistance. So let us assume that equal to around 2 kilo ohms. Let us start doing the design. So we know from the what specifications of this 7805, it requires minimum of 7 volts here. So let us assume that so they should have 7 to 20 volt as the voltage that is required over here. So let us try to assume a voltage of around 10 volt minimum. So 10 volt minimum, which is certainly more than 7. So we know that once you have a capacitor and a input impedance of 7805 acts like a resistor, the waveform at this point, suppose if you say this as V2 dash, the V2 dash waveform will be something like this. So that will be keep going like this. This is the waveform what you will be having. So what is this 10 is? So this should be minimum 10. So this is minimum 10 volt. And let us have a what ripple voltage of around 0.25 volts. So this naturally happens to be 10.25 volt. So now this is minimum. So if you are looking for a ripple of 0.25, the maximum is 10.25 volt. So this is 10.25 volt at this point. So at this point I have to have a peak voltage. I have to have a peak voltage of 10.25 plus 0.7, which is 10.95 volt as the peak voltage. So this is V1 dash peak. So now let us try to find out what is the standard value of capacitance, the transformer rating you can think of. So what I'll do is, so this is the peak voltage. So let me find what is V1 dash RMS. V1 dash RMS is 10.95 by root 2. So we can approximately take it as 11 by root 2, which happens to be 7.77 volt is the RMS value minimum required. We don't have a standard 7 volt or 7.7 volt transformer. Let us use the nearest possible, that is 9 volt transformer. So now what you can think now is this is 9 volt, 0 volt, 9 volt. This is what is the transformer rating you are looking for. So transformer rating what you have is, this is the transformer which will result in a peak voltage of, So this will result in a V1 dash peak of 9 into root 2, which will be 9 into root of 2 is 12.72 volt at this point. So this is what, on using this, you'll have 12.72 volt as the peak voltage, and over here it is around 12 volt peak. This is 12 volt peak. If it is 12 volt peak here, which is certainly more than 7 and certainly less than 20, so at the peak you won't have. So this is 12 volt and this is having a ripple of 0.25. So then this is actually 11.75 volt. So that is what is V2 dash peak. V2 dash peak is 12.72 minus V gamma, that is almost 12 volt, and V2 dash, okay, this is minimum. V2 dash minimum is, so that is 12 minus ripple voltage. V ripple is 0.25, you will end up with 11.75 volt, which is certainly more than 7 volts, so that you get a proper constant voltage of 5. So to have a ripple voltage of 0.25 for a full wave rectifier, so what is the value of capacitor? So that's what is the next design. So we know that P ripple is equal to the peak voltage at this point, which is P2 dash peak, P2 dash peak divided by 2FRC. So this is 0.25 is equal to V2 dash peak is this 12 by 2 into frequency is 50 hertz. 50 hertz is input frequency. So this we have assumed it as 2 kilo ohm, and we need to find the value of C. So C value comes out to be, so it is now 0.25 alpha equals 12 divided by open. It is 2 into 50 into 2 exponential of 3 into alpha A, close, shift cal, will end up with as 240 microfarad. 240 microfarad. So now the design involves a transformer of 909 transformer. So I have to use 240 microfarad capacitor. So, and of course 7805. So let me see that. Okay, I've rigged up the circuit here. This is the circuit what I'm having. This is the transformer. You can see this is, you can see here the rating of the transformer is, let me just take out this. So this is 909, corresponds to 9 volt RMS center tap, and again 9 volt RMS. You can actually measure what is the RMS voltage of this. The RMS voltage of this, instead of 9 it is coming as 10.2, 10.19, 10.26. So this is actual RMS. So let me start writing the values here. Now what I have is V1 dash RMS. V1 dash RMS is 10.3 volt. 10.3 volt. That's what is here. You see, I'm using. Let me just take out this. See, I'm using all the 3 terminals. If you can carefully notice this, you can forget about this. I have connected the bridge here. So one of the terminal, so one end of your transformer, one end of the transformer is directly going to, this is your diode. You can see I have 2 diodes here. This is anode cathode. You can see the 2 cathodes are shorted, and this is the junction point. And I'm connecting the capacitor of 220 microfarad is the standard value that is available in my lab, and I've connected the input of the regulator here. The output is connected here. The ground is connected to this. So this is your common ground. So this is the ground point. You see, center tap of your transformer becomes the ground point. Now input as one edge of, okay, one extreme of your transformer is going to anode. The other extreme is also going to anode. You can see these are the two anode connections, and this is center tap is going to this ground, and you can see these two cathodes are shorted and disconnected. This is where you're going to see the ripple voltage. That's exactly this point. This is that ripple voltage. You can see the input of your regulator is connected to the same junction, and this is the output point that is over here, and the ground is connected to this. So now let us see the voltage at input with respect to ground here, and then over here, and then we will just compare what is the waveforms you are supposed to get. So now let me just go to this circuit. Okay, I'm already having this, so let me make this. That's the number of cycles. Maybe this is fine. See now, let me stop this. Let me stop this. Can you see this is your input voltage? This is not a pure sinusoidal signal. That's what is I'm having in my supply. So this is the input, a sine wave, and you can see this is the output having some ripple, I can actually measure the ripple voltage. So if you want to see the rectified signal, so what I'll do is, how do I see the rectified signal? So let me just come back here. To see the rectified signal, I have to take out this capacitor, I have to put a resistor. So since we assume that, okay, since there is a effective resistance from here, what I'll do is I'll simply take out this capacitor. You can see a fully rectified signal here. Just carefully observe here. So let me show you both of them simultaneously. This is the circuit what I have now, and this is the waveform what I'm having running simultaneously. The moment I take out this capacitor, you can see I'm just removing this one end of the capacitor. Can you see that is becoming like, okay, just a minute. Can you see this is coming like a rectified signal? Just a minute. Can you see now? Now what I did, I simply, you can see this one end of your regulator, one end of the capacitor is removed. So the other end is there intact. Now you can see this is a rectified signal. This is a full wave rectified signal. So this difference is your diode drop, which we assumed to be 0.7. You can actually measure what is this difference of this and this, which I can do it here. So what I'll do is I will measure the channel 2 maximum, and I will measure channel 1 maximum. So the difference of the two maximum, okay, I'll just take out this. I'll take out this. See, difference of this and this, 14.222 minus 13.6, which is approximately 0.6, is the diode drop. We assumed it to be 0.7. It's fine. So that's what is a full wave rectified signal, which you are observing by removing the capacitor. You can see by removing the capacitor, by removing this filter capacitor, you are getting a full wave rectified signal. So what I'll do, I will put back the capacitor. I will get this ripple. Since this ripple voltage is very less, here my notebook, I'm just showing that variation very clearly, but in your scope, it will not be so clearly visible because this ripple is hardly 0.25 volts. So what I'll do now, I'll just make this also equally half, so that now when I put this capacitor back, see, just carefully observe this waveform. Can you see that waveform has become a filtered output? You know, I just connected back. So this is my filtered output. Now there's no question of this maximum minimum. I'll just take out this. You just concentrate on this peak to peak. So what I do is I will clear all. Let me add channel 2 peak to peak. Channel 2 peak to peak. So that is my ripple voltage. Okay, this is so many times it has been added. Oh, just give me a minute. Define measurement, channel 2, vertical, peak to peak, done. You can see this is the peak. if it is keep fluctuating, so what you can do is you can just have more number of waveforms so that it will be clear. Okay, now this is what is around 200 millivolt is the peak to peak voltage. So this is what we expected. This is what we expected here also. So we want to have, if you can see the minimum of this, so minimum of this we assumed it to be uh, 10, but we approximately got it as 11.75 from this 9 volt regulator, because now this is 9 volt transformer. It's not 9 volt now, it's 10.5 something, because that's what we got when we actually measured the voltage of this. So they should be close to 11.75 or slightly more than that. That is the minimum of this. So how do I do that? Let me just go to this defined measurement channel 2. Let me see the minimum. This minimum voltage should be more than 7. If it is more than 7, then you are fine. So now, so this is the output of this filter. Now let me see this filter output and the output of your regulator. This filter output becomes the input to the regulator. So what I'll do is I will take out this input signal. I will use uh, the channel 2 as the output of your regulator and channel 1 as the input to the regulator. Usually we always use channel 1 as the input. So what I'm doing now, so channel 1 is, this is yellow color is, or orange color is channel 1, which is the input. What you can do is, if you measure the, okay, let me just remove all, give me a minute. So I will remove all this. This is not required. I will take out this also. So let me add the average voltage of input and average voltage of the output. So if you can carefully note this, this is 5 volt. The output voltage is a DC voltage 5, even though input is varying around 13 volts. So what I'll do is I will go for this channel 1 vertical average voltage and peak to peak. Let me go to channel 2 average and peak to peak. If you can note this, let me just stop this. Carefully note the input voltage average is 13 volts. There is a peak to peak variation of 212 millivolts. The output average is 4.9981 volts, which is almost 5 volt. You can see the peak to peak variation is hardly 14 millivolts. It's fairly constant. The output voltage is constant at 5 volt. Even though input is varying too much, so it is having a constant voltage of 5 volts, because the input voltage is always more than 7 volts. Okay. So this is how you can able to perform a DC volt regulator using 2-diode Fourier rectifier. So let us continue this analysis for a bridge circuit. So for a bridge circuit, so we will do that over here. So what I do is, let us do the design part of your bridge circuit, and let us see what is the difference while measuring the signal from resistor. So now this is my, let me enlarge this. So this is the input voltage. This is again a 5 volt DC power supply design using bridge bridge circuit, bridge rectifier. So now we're going to have a step down transformer, then I'll have the bridge circuit. This is the bridge circuit. What I have, this is plus DC rectifier signal. So this is one input sine wave, this is another sine wave. Let me apply the input here. You can simply name it as D1, D2, D3, D4. During positive half cycle at the input D1, D2 will conduct. During negative half cycle, D3, D4 will conduct. And then we're going to have the filter capacitor, and then we'll have 7805. I can simply this is now you can see I can ground this. This is the ground. There is no ground here. So this you are using. Let us find out. This is V in. Let me say it as V1 dash. This is a 230 volt, 50 hertz AC signal. This is V2 dash, which is a filter waveform. This is input, uh, ground, and output. You will be getting plus 5 volt. So now we need to, of course, design what will be the rating of this. So now, as we know that this is 5 volt required, you need to have 7 to 20 volt as the voltage. So let us again assume it as around 10 volt. So as we did in the previous case, so can we just use the same thing? So at this point, I should get the 10 volt here. So now the difference between this 10 volt and this, we have it as this is 10 volt plus a ripple voltage of 0.25 volt, and when it then the peak, this is minimum. So this is what we have. This is 10. So if you have a ripple voltage of 0.25 volts, then this is 10.25 volt. So this is 10.25 as we saw in the previous case also. And then if you want to go back here, so we were adding 0.7, that is the peak of your V1 dash. But what is V1 dash peak? It is 10.25 plus 2 times 0.7, 2 times of 0.7. So why it is 2 times? Because 2 diodes are conducting at a time. So the voltage at this point should be 10.25 plus 2 times of 0.7. So that is 10.25 plus 1.4 volt, which has to be 5, 6. This is 1, 1. So you should have 11.65 volt as the peak voltage at this point. So I want to have 11.65 as V1 dash peak. V1 dash peak. So then what should be its RMS? V1 dash RMS. V1 dash RMS has to be, it is V1 dash peak by root. Correct? So it is 11.65 divided by, okay, sorry, it is root of 2. It is 8.23 volt. So since this is closer to 9 volt, we can still use now 90. This is 90 enough. It's not 909 required because you don't want to have a center tap transformer. If you have 9 volts, that is enough. So now I'll be using 9 volt and 0 volt. So this is the transformer I'm using. I'm not using the another 9 volt also. So I will just suppose if you are using a transformer something like this, even though this is 909, I will use this 9 volt terminal and this 0 volt terminal. So suppose if you assume that even if I have something like this, so this may be 909, I'll be using 0 volt as my reference. Okay, so I'm using 9 volt transformer. So this is what is. So if you're using 9 volt, then what is V1 dash? What is V1 dash RMS? V1 dash RMS is 9, and V1 dash peak is which is 9 into root 2. 9 into root 2 is 12.7, and at this point, by the time it comes over here, that is V2 dash maximum would be 12.72 minus 1.4. Why it is minus 1.4? Because 2 diodes drop together. So that minus 1.4, which is 11.37 volt, which is certainly more than 7. Of course, this will have a what, minus 0.25 as your ripple voltage. So you still have close to 11.12 volt as the V2 dash minimum. V2 dash minimum. That is this voltage will be 11.12 volt, which is certainly more than 7, which is minimum required. And this is also be not very large. It will not be more than 20. This is close to, so 11.12. So since it's 11.37. So since 11.37 and 11.12 are between 2 and 20, you're supposed to get a proper waveform. Okay, let me just demonstrate that now. So now let me use this same transformer rating. Now you can see I can remove this 909. I'll be simply using. So let me just, okay. This is my 9 volt. I will connect it to this is my rectifier. Sorry, bridge circuit. So bridge circuit is actually looking something like this. This is going to have a 4-terminal component. So this is where you'll apply the input. This is where you'll see the output. So can you see this is plus minus? This is sine wave inputs. The symbol goes like this. The symbol of your bridge, it's a symbol of bridge looks like this. So this will have a shape like this, and there is a plus symbol, there is a minus sign. This sine wave indicates you should apply AC input. There is a AC input, and this plus is your DC voltage plus, and this is DC voltage negative. This is exactly similar to this. Can you see here? This is that sine wave. Can you see this is the sine wave point. This is the sine wave point. Can you see this is plus, this is minus? So in this if I say this as 1 2, then this is 1 2. If I say this is 3 4, then this is 3, this is 4. So this is how we are connecting. That's what is this here. So let me just take out this 2 diodes to not to confuse you all. I'm just removing this. So I have this. Can you see this is sine here? If I just take it closer to you, this is sine. This is another sign. Can you see this is plus, this is minus? So I will use this. So one end of your input is going here. The other end of the transformer output is going to this sign. And whatever plus I have, whatever plus that I'm having, will go to the filter. Can you see this is my filter? So this is filter here. I'm connecting it to filter. This minus will go to, can you see this is minus? The minus will go to, I will connect the negative to this. You can see I will be connecting this minus. This is connected here. Now this is my this is the output point where I'll be seeing the output. Fine. So this is perfect. So let me see the input and output. That is okay. One thing you have to be very careful while observing the waveform. Let me rewrite the circuit again for clarity here. So this is the transformer input. This is the output of the transformer. I'm using this and this. This is my bridge circuit. Let me write the bridge circuit like this. This is, and this is plus minus. So one, this is going here, and this is going here, and this is where you see the output. This is your output point. So here I'm connecting capacitor. This is I'm connecting capacitor. This is my 787805. This is what. So now this is ground. See, there is a total isolation from input and output. So now if I want to see the input, so I need to connect the plus here, minus here. If you want to see the output, I have to connect plus here, minus here. You can see this minus is different from this minus. So when the grounds are not same, I have to use C1 plus here. This is C1 minus. This is C2 plus, and I can use ground here. So since C1, since the negative of your input and negative of the output are not same, I have to exclusively use C1 plus, C1 minus terminals of my ADK to differentiate the common terminal. So this is C1 plus, which is connected to the transformer. Okay, this is the transformer here, and I will use a C1 minus. Where is C1 minus? This is C1, that is orange with a yellow strip, sorry, white strip. So that will be connecting it to. So let me use. So this is, where is it? Orange with white strip is here. Okay, this I will be connecting it to other input terminal, exactly this. So I'm connecting C1 dash, sorry, C1 plus and C1 minus. See, this is input. So across two inputs I'm seeing. So this is what is, okay, let me run this. See now, this is the input signal. So meaning I connected C1 plus, just a minute, I'll show you. This is C1 plus, C1 minus. I'm getting the sine wave here. So I'm seeing the sine wave here like this. And let me see C2 plus. I'll connect only C2 plus and I'll ground it. So where is ground? This is ground is already connected here. So C1 plus is blue wire. So that I'll connect it to, that will connect it to the capacitor. Here, since the cycle what I'm having is with the filter, if the filter is intact, I will see a waveform which is filtered. Can you see is already filtered? So what I'll do, in order to see the rectified signal and the voltage is less by the 2 times of V gamma that you can observe now. So let me show you that. So what I'll do is, okay, I will make it lesser number of cycles so that you can clearly see. See now what I'll do, I'll take out the capacitor. The moment I take out the capacitor, it's like, okay, taking out the capacitor, you will have a fully rectified signal. See, I'm taking out the capacitor. Can you see the moment I take out the capacitor, you have this rectified signal. Carefully note this maximum and this maximum are away by almost 1.2 volts or 1.4 volts. Can I do that? So what I'll do, I will measure that. So I will measure channel 1, channel 2 maximum and channel 1 maximum. The difference of these two, can you see the difference of these two is almost 1.2 volts, which is twice the diode drop, because two diodes are involved in uh, the power dissipation. Sorry, diodes are involved during the conduction of each of the cycle. So that's why it is the difference is almost 11 point. Sorry, the difference is 1.2 volts. So that's what we have now. So now we'll just, I'll put the capacitor back. I'll put the capacitor back and I'll see the rectifier signal. Can you see now? So not the rectifier, the filter signal. Can you see now the filter signal is there? Now you look for the ripple voltage. So what I'll do, I'll take out this. I will remove this. I will remove this also. Now you see, okay, this is your filter signal. So I don't want to see what is C1 peak to peak. Can you see C2 peak to peak is this much? 200 millivolt is the average, sorry, the peak to peak voltage. C2 is actually the peak to peak of this, the ripple voltage, which we assumed to be 250 millivolt, which is almost close there. So if you increase the number of cycles, you will get it close. You see it's almost 210, 20 millivolts. So this is your filter signal. Exactly, you are looking the waveform at this point. Where is This is the point. This is the point of interest we are looking at. This is what we are seeing. This is what we are seeing. That is this type of filter signal. So now it is always above 7 volts. So you are bound to get exact 5 volt at output. Now we will see this input to the regulator and output to the regulator. So I will use second channel here and I'll use first channel here. So now first channel with respect to ground, second channel also with respect to ground. There is no need of C1 minus now. So what I'll do now, let me come back here. I will simply use C1 plus here, C2 plus here. I'm not using C1 minus anywhere. You can see that's what I'll do. Can you see this is C1 minus? C1 minus I'll simply take out. C1 minus I don't want. C1 plus I will use it at the input of the regulator. At the input of the regulator with filtered output. This is the input to the regulator, that is filtered output. So this is the regulated output. This is C1 plus C2 plus. So this is the input to the regulator. This is output to the regulator. Exactly, I'm saying C1 plus here, C2 plus here. This is the input to the regulator. This is output to the regulator. Here I'll be getting a waveform which is filtered, and here it is a constant 5 volt. This is 5 volt. This is around 13 volt is the RMS voltage. Is that? Let me go here. You know, are you getting a constant 5 volt? This is a constant 5 volt. This is having a ripple of around almost 12 volts. Almost 12 volt. Can you see this is almost 5? 4.999. So this way we can able to do the DC power supply of 5 volt using bridge. Just before this we spied how do we do it using full wave 2 diode rectifier. So the major difference between 2 diode full wave rectifier and bridge is, for bridge there is no need of center tap. So meaning only two terminals are enough. Only two terminals are enough. For a 2 diode full wave rectifier you need to use all the three terminals. So this terminal is not required when we are doing full wave rectifier. And of course this is what is the advantage. Thank you.